So, energy doesn't really explain why things happen like forces do. Forces are used to determine what drives a system forward, why things move, how they move, and so forth. But energy gives us a new way to tell the story about what's happening. Thinking about the energy stored due to an object's motion or due to its position is incredibly useful and allows us to predict things that we could not predict using our basic ideas of F equals ma. Energy is tracked by looking at changes in motion and changes in position. Sort of like having a scorecard out there that just watches how the types of energy transform as an object moves. We talk about kinetic energy, symbolized by a capital K, as energy stored because an object is moving. And so anytime you have some sort of object, some mass that has a speed, has motion, we would consider it having kinetic energy. We'll also talk about potential energy. Potential energies, there's actually quite a few different types. We'll talk about two in this class. The symbol capital U is used to represent potential energy. You might think, well, how come we don't use P? It turns out there's a lot of other ideas, a lot of other quantities in physics that also start with the letter P. And so we have to make some choices. Capital U is standard for potential energy. And if that potential energy is due to a gravitational field, meaning the area around a massive object like the Earth, then we talk about gravitational potential energy. And so we use a little subscript G to represent that. We'll also eventually talk about elastic potential energy. This is energy that is stored because something has been stretched or compressed, something like a rubber band or a spring. These sorts of ideas of potential energy all have to do with where an object is, what its position is. Kinetic energy has to do with how fast something's moving. Those are the two main ways of describing an object's motion within the mechanical world. Kinetic energy, again, is going to be energy due to motion. So this little girl, as she slid down the slide, she gained kinetic energy. And at the bottom, she would only have kinetic energy because she's at her lowest point. At the very top, before she began to move, she had all potential energy, specifically gravitational potential energy. She's above a lowest point in the system, above the ground. But all along the way, as she's sliding, she would have both types of energy, both kinetic and potential. And our class will mainly focus on these two, and again, adding in elastic potential energy at times. Kinetic energy is calculated using the mass of the object and the speed. It has to do again with motion, and so the greater an object's speed, bigger the V is, the more kinetic energy it has. But also, if it's just a larger object, it has more mass that is moving at that speed. That is also going to be associated with more kinetic energy. So the formula is 1/2 times the mass in kilograms times the speed squared, with that speed measured in meters per second. It's really important that you have those standard units in there, because that together, when you take a kilogram and you multiply it by meters per second squared, that is defined as something called a joule, and that's our standard unit for energy. Gravitational potential energy depends again on the object's mass, but also on where it is compared to the Earth or whatever other large object we are considering. When you raise something within a gravitational field, when you move something further away from the Earth, its position is raised and its gravitational potential energy is increased. So at greater heights, objects have more gravitational potential energy. And we tend to use the ground as our zero value for potential energy, but it really just has to be whatever the lowest point is that the object will reach. Again, mass is important. The bigger the mass, the bigger the potential energy. All of these forms of mechanical energy depend on an object's mass. But if you did go to someplace other than the Earth, the gravitational field would change, and therefore the gravitational potential energy would change. So for instance, on the moon, little g has a smaller value than on Earth. And so an object a certain height above the surface would have less potential energy on the moon than it would have on the Earth. Now, the units for potential energy are, in fact, the same as the units for kinetic energy. It's a joule. Let's see why that is. If we plug in standard units into this formula, we would be taking kilograms for mass, newtons per kilogram for little g, and meters for y. You can see that the kilograms cancels out and we're left with newtons times meters. But a newton is not a basic unit. It's a derived unit. It comes from combining other simpler units. If we think about F equals m times a newton should equal the units of mass times the units of acceleration. So that would be a kilogram times meters per second squared. And then if you just kind of mush these together a little bit, you do get that same expression of kilograms times meters squared per second squared. That is what a joule is defined as. So again, potential energy is measured in joules. All forms of energy will be in joules. Now, there's one more type of energy that we're going to talk about, and it is the energy having to do with elastic materials, meaning things that can be stretched or compressed, like the spring or a rubber band, or really even like the muscles in your body. Okay, anything that can stretch or compress is what we would consider to be an elastic material. And those materials are defined by something called a spring constant or a force constant. And this is a number that represents how hard it is to stretch or compress that elastic material. The symbol is a little k, which is unfortunate because, of course, we have capital K for kinetic energy. But I can't change the rules here. So it's a lowercase k with a little s to help us remember that it is referring to the spring constant. And again, it indicates the resistance, how hard it is to stretch or compress something. It's measured in newtons per meter, meaning how much force is needed per meter in order to stretch something or compress it. This spring that's easily moving up and down like this would have a pretty low value of K sub S. It's easy for it to spring up and down or to move up and down, and so the resistance is low. But inside a car, not inside a car, but near the axles of a car, there are going to be shock absorbers that can withstand a large amounts of sort of bounce within the car. They will have very high values of K. It's going to be very hard to stretch or compress those particular springs. So because these elastic things can change their position, they can also hold energy, and we do call this a potential energy because it is stored within that system. So we will continue to use U for potential energy, but instead of U sub G for the gravitational potential energy, here we have U sub E for elastic potential energy. And again, this is energy stored when an object is stretched or compressed. So we're thinking springs and rubber bands, things like that. If K sub S is bigger, like that shock absorber was, you can store more energy in a spring. So the bigger the K, the harder it is to stretch or compress it, the more energy is stored within it. Also, depending on how far you stretch or compress, that increases the amount of energy stored as well. We're going to use a delta X to represent that stretch or compression. And you might think, well, Doesn't it matter whether if it's being stretched or being compressed? In fact, it doesn't, because the formula for the elastic potential energy involves squaring that delta x. So no matter whether it's getting smaller or larger, it's going to be squared, and so the overall value is going to always end up being positive. This type of energy, like all types of energy, will be measured in joules, capital J.